Anyway, I would like to talk today some more about Euler circuits and a related thing. I hope you remember about Euler circuits and Euler paths. So, the question of does an Euler circuit exist or not is very easy. I got baked goods.
Oh my God.
Are you interested?
I like these.
The question of is there an Euler circuit or not is very easy to answer, right? Remember, Euler circuit uses every edge, no repeats, right? That's the point. But on a typical graph, like usually if I just show you a graph at random sort of, it probably will not have an Euler circuit because Euler circuit requires all of the edges or all the vertices have even degree, right? So Euler circuit exists, I hope you remember this, if all the degrees are even. And so I would say this, can I just say, this usually won't be the case, right? Like the graph has to be a very particular way in order for all the degrees to turn out even. Like typically you would expect, some of them to be even and some of them to be odd. So Euler circuit exists if all degrees are even. And remember, we also talked about Euler path. And the rule for that was if all are even except for two odds. And this also usually will not be true. You have to just kind of get lucky for there to be only two odds and then all the rest to be even, all right? So I will say, again, usually not true. In a typical graph, you'll have a mixture of evens and odds. There's no reason for all the degrees to be even in a typical graph. Yeah?
Are we having a final?
Yes?
Okay. Do you know what day?
Yes? It's on the syllabus. I don't remember
Okay.
off the top of my head. Yes. We are having a final. Yeah, every class is supposed to have a final. I have to get special permission from the dean if I want to not have a final, which is
Oh,
a
really?
little ridiculous in my opinion, but
Yeah.
yeah. Yeah, you should, all your classes have finals unless,
Yeah, no, just
unless
some
they
of my
don't.
teachers have like unless if it's in the syllabus, then no one's saying anything.
Oh, yeah.
Yeah.
Okay, Euler circuits and paths. What I'm trying to say is for most graphs, there isn't going to be an Euler circuit or an Euler path because they require that the degrees be this very, very particular way. Okay, so for typical graphs, you cannot do this business about use every edge with no repeats. All right, so what I want to talk about today is what about in a graph where this is impossible? Can we figure out how to do like the best possible? So no repeats usually is not possible. I'm going to say even when these don't exist, come on, even when these don't exist, we often want paths and circuits which do as few repeats as possible, right? If you're in some kind of real world scenario where you want to do no repeats at all, that's usually not possible. So the natural thing to go for in that case would be, all right, we can't have no repeats, but can we have like the minimum possible amount of duplications, all right? And that there's a name for that. So this is called it's a fairly self-explanatory name, minimum duplication circuit. A minimum duplication circuit or minimum duplication path, right? So what that means is it uses every edge and repeats as few as possible. Maybe you can do it with no repeats. That's called the Euler circuit, but usually you can't do it with no repeats. The best you can do is called a minimum duplication circuit. So what we're going to talk about for today is, I give you a graph. Can you, first of all, figure out how many edges you're going to have to duplicate, and then, actually find the minimum duplication circuit. So here is an example of sort of where we're going. Actually, we don't know enough yet to say precisely what the answer is here, but this is a graph which, first of all, when you look at this, does it have an Euler circuit? Let's just talk about circuits. It does not, because I look at the degrees. That's a 2, that's a 3. So I see odd degrees, which means there is no Euler circuit. That's what the degrees would look like. So Euler circuit is impossible. That means that any kind of circuit must repeat some of the edges. If you're going to cover every edge, we must have some duplications. So we must have some edge repeats. How many? Can you do it with only one repeated edge? This would be, I suppose, the best case scenario. If you can't do it without any repetitions, maybe you can do it by repeating only one edge. Actually, just because I know how to do this already. This one, you cannot do it with only one repeated edge. In fact, in this example, this one requires 4 repetitions. But this is where we're going today. We don't know how to do this yet, but this is the idea. There is a method by which you can look at the graph and figure out, it has to do with the degrees. Look at the graph and figure out how many total repetitions would it actually require. And in this particular example, just because I know how to do it, you have to repeat at least 4 edges if you want to cover all the edges. All right, this is where we're going today. So let's start with a simpler example, and maybe we'll come back to this one later on to see how that one plays out. Here's a simpler one. How about this, like that? All right. In this one, first of all, again, you look at the degrees, and you notice it's not possible to do a circuit, an Euler circuit. Hey, it's not possible to do an Euler circuit here. I got baked goods, even for people who came late.
Oh, really?
Yes.
Thank you. Sorry.
I have one. Here's the napkin.
Please. Thank you.
Mm-hmm. It's pumpkin. Real. I made it with real pumpkins.
Oh, you made it yourself?
Yes.
Nice.
Okay, so you see the odds, right? So this one has no Euler circuits, which means some repeats will be required in order to do a circuit. Some repeats are required in a circuit. All right, can you do it with only one repeat? Actually, in this example, you can. What you want to think about when you look at the graph is I identify these 2 3s as like the bad guys, right? Those 3s, the fact that they are odds, that's the reason why there's no Euler circuit in this graph, all right? Those 2 3s are bad. Can I just say we need to kind of fix the odds, by which I mean make them into evens, by doubling up certain edges, by edge doubling. Is there any edge in that graph that we can double, which would turn those odds into evens? What I mean by edge doubling is just, well, in this case, it's this edge that connects the 2 odds. If I were to turn this single edge into 2 edges right next to each other, I'll put this in blue. All right, that's sort of a fictional edge. I just added a new edge in there. But now it turns this 3 into a 4 and this 3 into a 4 because I made one more edge right there, all right? And now in this new graph, all the degrees are even. And so now it is possible to make an Euler circuit in this graph. So the strategy here is double edges to make all the degrees even. All right. And in this particular example, if I do that, I end up with this graph here. Right? It has two edges going across the middle instead of just one, because I doubled up that edge. Double edges to make all the degrees even, and then make an Euler circuit. Because now all the edges are even, and so I should be able to actually make an Euler circuit, that is one which has no repetitions. So on my new graph here, with the extra edge across the middle, maybe I'll start over here and I'm going to draw an Euler circuit. I hope everybody remembers how to do this. This is a small graph, so it's not difficult. I can go up here, around this way, maybe across the middle, and back like that, right? So I just drew an Euler circuit in my slightly modified graph, and now this circuit, do this circuit on the original graph. And what it looks like is, the original graph, remember, has only one edge going across. And what that same circuit on the original graph looks like is it's a circuit which repeats one of the edges, right? Goes across that middle edge twice, but all the other ones only once. So I do this circuit again on the original graph, and it looks basically the same. Up like that, down here, across the middle, back across the middle, and around the bottom. All right. And now this is a minimum duplication circuit. It duplicates one of the edges, the one across the middle. All right. So this is a min-dup circ. Minimum duplication circuit. It duplicates one edge going across the middle and otherwise covers every edge. All right. This is the way that we find minimum duplication circuits. How do you know this is the minimum? Like I did one repeated edge. I know that's the as small as possible because we already know it's not possible to do 0 repeated edges, because that would be a Euler circuit, which you can't do in this particular graph. All right. So this process here, this doubling the edges to make all of the degrees even, this is what we're going to think about in more examples here. So we need to double edges to make all the degrees even. Usually you can do this by thinking of the edges in pairs. So here's another example. This is like a big tic-tac board. Tic-tac-toe. Not TikTok. We need to double the edges to make all the degrees even, right? So first, when you look at this graph, you should first decide what all the degrees are, with particularly focused on the odd ones. That's what you care about, but you're gonna have to look at all of them anyway. So I got 2 3s there, a 2 in the corner, a 3. They got 4s on these inside ones. 4 4 3 2 3 3 2. All right. So those are all the degrees. I hope that everybody by now is good at telling what the degrees are for each vertex. And focus on the odd ones. Those are the ones that you need to sort of repair. So they are here. I see 8 odd ones. All right. And you want to decide for yourself the best way to double up edges in a way to make them all even. I'm going to say, if possible, connect 2 odds with an edge. So for example, I see these 2 3s up top. I'm going to make just double the edge going in between them. That turns them both into a 4. Because every time you double up one of the edges, you're going to increase the degrees by 1 each. So I'm going to double this one, which makes a 4 and a 4. And then I'll just pair up each of the odds. That's the best way to do it. I see the 2 3s on the left. I'm going to double that one up, which makes a 4 and a 4. the 2 3's on the bottom, I double that up, which makes a 4 and a 4. And the 2 3's on the right side, I double up, which makes a 4 and a 4. All right. So, if possible, connect 2 odds with an edge. I say, pair them up. If you can pair them up, then you can just add new edges, and every time you add one of those edges, it turns 2 of the odds into 2 evens. All right. And there's no better way to do this. Here, I had to double up 4 edges, which made everything even. And there's no way to make them all even using any fewer than 4 edge doublings, because every time you double an edge, it fixes 2 odds and turns them even. So this is the best way to double up the edges on this graph. And then you would draw an Euler circuit on this graph to find a minimum duplication circuit for the original graph. So I'm going to draw this graph again, but with the doubles here, 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 and here. There's a name for that. This is called the Eulerized, also called Eulerized by some fools. This is the Eulerized version of the graph. And this one does have an Euler circuit because all the degrees are even. And when you find an Euler circuit here, it's the same as finding a circuit on the original graph which duplicates some of the edges. And you can tell actually which of the edges are going to have to get duplicated. They're these ones that I doubled up here. All right, that was a signal that when I actually draw the circuit in there, I'm going to go across those edges twice. So, and I hope you remember how we talked last time about how to draw the Euler circuit. I'm just going to try and draw it in here. Remember, the strategy is you have to make sure as you're going you never cross over a bridge among the remaining edges. So there are many, many ways to do this. I'm going to try and do it. Don't cross a bridge. And of course, you can't repeat edges, except unless it's those ones that I said I was going to go over twice because I doubled them up. I hope I'm doing all right here. I'm just trying to make it, as I go, I'm making sure that all the edges I didn't hit yet are all together. They're not disconnected into 2 portions. All the remaining ones are down here, which I feel good about. Over here, like so. All right, so you can see there are 4 times that I went back across the same edge. They are these doubled up edges, here, 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 and here. And otherwise I hit everything once. All right, so in this case, this is the minimum duplication circuit. Requires 4 dupes, right? 4 duplicated edges are necessary in this particular example. All right. Any questions, thoughts about that? All right, let's just look at a few more examples. How about something like this? Something a little weird can happen when you do these. This is an example where something slightly weird happens. Let's see. Anyway, you begin by looking at all the degrees, as we always do. So I put 2's here. This is a 3, a 4, a 2, a 2, a 4, a 2, a 2, a 3 here. 4, a 2, a 2, a 4, a 2, a 2. All right? It looks like we have 2 odds and the rest are evens. And we have to decide which edges to double in order to make the odds all even. And what's interesting about this particular example here is we have 2 odds, but they're not connected by an edge, right? They're kind of like far apart from each other in this graph. One is over here, and one is all the way over here. So you cannot just double an edge between these because there isn't just one edge. That means you're going to have to duplicate several edges. They're not connected by an edge. What you have to do here is duplicate all edges along a path connecting them. So these two, the 3 here and the 3 here, you cannot just duplicate a single edge, and you're not allowed to invent a new edge which was not already in the graph. You have to do this by duplicating existing edges, because our goal is to make a circuit which duplicates some of the edges. So since there is no single edge from this 3 to this other 3, you have to find a path from this 3 to this one and duplicate each of the edges along the path. So the most obvious way to do that is like this. I duplicate that edge, and also that edge. This is how you have to do this when your two odds are not next to each other, but they are separated by a few other edges. Let's just think about what does that do to the degrees. Each of those 3's becomes a 4. It also changes these 4's though. It messes up these 4's, which should worry you that you don't want to create new odds when there used to be evens. But actually, I added 2 edges to this 4, so that which used to be a 4 is now a 6. And this, which used to be a 4, is now a 6. So it's okay, they're still all even, all right? So when you have your 2 odds which are not connected by an edge, the way that you Eulerize the graph, that is duplicate edges to make them all even, is you have to find a path connecting one of your odds to the other one and duplicate all the edges along that path, all right? So in this case, this one requires 3 dupes, right? 3 duplicated edges. There's no way to do it with only 1 or 2 in that particular graph. All right. Maybe we could look at this point at the thing that I started off with. This one here. This one, if you look at the degrees, they're 3's and 2's, right? And a 4 in the middle. And unfortunately, in this case, you cannot just connect the odds up in pairs. You may be tempted to say, can I just, so you say, all right, the odds are here and here and here and here. Those are the ones I have to make even. You may be tempted to just add a new edge like that, a diagonal edge. Then that makes those 2 odds into evens. That is not allowed though, because what we're doing by creating new edges, they are meant to represent duplications of the original edge. You cannot just make a new edge between 2 of them. You have to duplicate existing edges. Duplicate edges. Don't create new ones. Or you can create new ones, but they have to be copies of the original edges. You can't create a new edge which never existed before, such as a diagonal. All right, so in this particular example, your only option, if I want to say connect up these 2 3's, you cannot go straight across the diagonal. You have to duplicate 2 edges like along a path. I could take this, go around the corner here, all right? Or I could go through the center, which also requires 2 edges to match up those 2 3's. So now this 3 is a 4, this 2 is a 4, and this 3 is a 4. And then to repair the other 2 3's, I have to do a similar thing. You have to duplicate 2 edges, either going the outside corner or you could go through the middle. Either way, it's going to require 2 additional edges. So that is a 4, that is a 4, that is a 4. So anyway, we need 4 duplications. This is what I was sort of looking at in my head at the beginning of class when I showed you this example. There were 4 odds, but they cannot be just connected simply in pairs. So you have to actually duplicate 4 edges in that particular one. All right. This is how you know how many duplications are necessary. Here's just one more example, and then I have some for you to try. Do I? Yes, I have some for you to try. How about this? This is an especially bad one in that it requires many duplications in order to make all the degrees even. But so if we look at this, what are the degrees? Here I have a 1. The thing in the middle is a 3. I'm going to write these in black. 1, 3, 2, a 2, a 1, and a 1. All right? So focusing on the odds, which are here, 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 and here. Can you pair them up, or do you have to duplicate several of them? You can't really pair them up. You could pair up the 1 and the 3 here by making an extra one like that. But then you have these two 1s, which are separated quite far from one another. You're going to have to double up every edge along a path from one of them to the other. So in fact, this is kind of like the worst case scenario. You actually have to double everything in order to repair all the odds in this particular example. You have to double up everything. So this 1 now is a 2. This is a 4. This used to be a 3, has become a 6. That's a 4. That's a 2. That's a 2 also. All right. So here we had to double everything. And this is the worst case scenario. Certainly it will make everything even if you just double up every edge. Then all the odds will become even. But that's the worst case. Had to duplicate all of them. All right, that is 5 duplications, right? In that example. Okay, so here's the strategy. Let me just try and write a little summarizing here. Eulerizing by edge doubling. All right, so first of all, you identify the odd degrees and you try to pair up the odds, and you duplicate all edges on paths. Connecting the odds. If you get lucky, the odds are just already next to each other along a single edge, so you just duplicate that one edge, but sometimes you'll have to duplicate more than one edge at a time in order to make it all work out. All right. And this is how you can draw minimum duplication circuits. I got some simple ones for you to try, so try these. So there's one. Decide for yourself which edge am I going to have to duplicate, or which edges, and then try and actually draw the minimum duplication circuit. As usual, there are more than one way. There's going to be more than one ways to do it. Find a minimum duplication circuit there, and I got one more. And maybe I'll make up another one over here. There we go. That last one I drew kind of small. Draw it bigger when you draw it. So your final answer should look like a circuit which duplicates some of the edges. should.
To draw this.
Yeah, you should actually draw it in also.
Okay.
Okay. Mhm. Anybody want another one of these? Alright.
Yep.
You should, so your actual answer should be, like, actually draw the circuit.
Okay.
You should actually draw the circuits in, which duplicate as few edges as possible.
Do you want us to draw two about the duplication or just draw what?
Whatever.
Okay.
So good?
Oh, is this? Oh, I don't want it right here.
Yeah. I mean, this is ready for.
For this drawing, but I can do that one too.
Still doing good? So you paired up those two?
Yeah.
That's good. No. So, yes, in theory, you should be able to throw 2 by 2, right? Did before. Say, like, take this and that together. No, like, these two, like, here.
Yeah, yeah. Sweet.
would say you want to pair them up. So maybe like take these two together, and then you have to deal with these two.
Okay.
Together also. Let's take a couple more minutes and then we'll chat.
This is what happened second. Oh wait, no. Okay. Never mind. I like can't find if you can't. Oh, you're okay.
That would mess up the ending.
Yeah. There we go. Thank you.
All right, let's talk about these. I didn't get to do the last one. That's all right. So this one here, a lot of people noticed that there are going to be sometimes sort of good ways to pair up the edges and also bad ways. In this case, you can do it by pairing up I have the 4 odds, right? And I can pair them up kind of 2 by 2. There's a few ways to do it, but I could do, say, there, which turns these to 4s, and then I have 2 more odds remaining, and I can connect them up with an edge, which turns these to 4s here. So that's the way that I would do that one, which means those 2 blue ones are where I'm going to duplicate. So, and then to draw the circuit in, I will just try my best. I'll duplicate that one right away. Come around here. Over here, and back there. So something like that. 2 duplications are necessary in that graph. And as I went around, it looked like everybody worked that out. Okay, and then this last one is bigger and maybe more interesting. Can I make it bigger? I think I can. No? I thought there was a little scale or something. How about this? Paste. Yeah. You gotta paste it first. Then you can make it bigger. Okay, let's try this one. So you look at the degrees first of all. There's a 3 here. Oh no. It doesn't like when you write on top of a pasted thing. There's a 3 here, a 3 here. And I think those are all the odds, right? So I would immediately decide to connect up those 2 because they are next to each other. These other 3s are not next to each other. You have to duplicate all of the edges along a path from one of those 3s to the other one. And which way should we go? I think the best way would be to just go, take the path going sort of straight down. So I need to duplicate 1, 2, 3 like that. So this is 4 duplications total, and I don't believe it's possible to do this with only 3. All right? You might wonder about what if instead I connected up, say, here and here to connect these 2 guys together, but then to get these 2 together, you're going to have to go a lot more. So I believe this is the best that you can do. 4 duplications here, and then maybe I'll try and draw in my circuit. Let's start here. Doesn't matter where you start, right, when you're doing Euler circuits. As usual, please make sure that your circuit is readable by me. That is, you have to be able to tell on your picture where it goes from one step to the next. I'm trying to draw it in here. You can more or less make this up as you go along, but remember the thing, this is what we talked about last time, you have to make sure as you're drawing the edges that you don't cross over a bridge among the unused edges. So as I'm going around, it looks like I'm just making this up as I go, which I kind of am, but I am keeping in mind where are all the unused edges. At this point, they're all over here in one connected bunch, and I am never going to choose an edge which disconnects them from one another. Oops, maybe I'll go straight down again. I'm doing okay, I think. Ooh. Up here, that's a duplication. Almost done. There, I finished. All right, 4 duplications in there. Your circuit probably looks totally different from mine, but I hope that you also did it with 4 duplications. Any thoughts or questions about that? All right, this is minimum duplication circuits. Let's just talk very briefly about what about a minimum duplication path? That's all the same stuff, but it doesn't have to be a circuit. It's a path. Let's talk about that. Once you know how to do it for circuits, it's really very simple to do sort of the same thing, but for paths. So minimum duplication paths. All right. This is sometimes, you'll see why, this is sometimes called optimal parade routes. Parade as in, you know, like the Thanksgiving Day parade. This is if you're trying to plan out where the parade should go, where should they start and finish. This is kind of related to minimum duplication paths. Anyway, let's just do this with an example. I will just say in words, same thing, but we leave 2 odds and make the rest even. Because that's what gets you an Euler circuit. An Euler circuit is they're all even, but to just get an Euler path, you can have 2 odds and the rest be even. So we do the same thing, but we leave 2 odds and make the rest even by edge doubling. Right? Otherwise, it's the same deal. It's just that you don't have to turn them all even. You can leave 2 of them as odds. So here is an example. This is a big example. This is sort of a street grid with some diagonals, a few diagonals. Here, here, and here. All right? Let's see if we can find a minimum duplication path. Maybe I don't want to actually find the whole thing, but can we answer at least how many edge duplications are necessary? In a to make a minimum duplication path. All right. These are called parade routes sometimes because you know, if you want to have a parade in this neighborhood, obviously you want the parade to go down every little street, so none of the little kids are disappointed that the parade didn't go past their house. So you want the parade to hit every edge, but you don't want extra edge duplications. You don't want the parade just like walking back and forth down every street. So how many duplications are necessary? That is, how many times is the parade going to have to go back across the same spot? And then also you can say like, which of the edges should we duplicate to make this work out the best? All right. The kids would want to know that too. Then they should set up their little chairs on the duplicated edges, and they get to see the parade go by twice. Anyway, we do this just like before. We look for the degrees first of all. This is all about the degrees, and specifically we should focus on the odds. So where do you see odds? I see a 3 here, and actually there are many 3s in this graph. It's everywhere you see a 3-way intersection is a 3. That's a 3 on that corner. That's a 3, a 3, a 3, a 3. I think I got all the 3s, all right? We have some 2s in the corner, some 4s on the inside, which are fine. This is a 4, a 4. Are there any more odds? Yeah, there's 2 5s here and here. So this a 5, that's a 5. Other than that, I think they're all evens.
What about the 5?
Oh, and here.
Yeah.
Yes, thank you. The 5 there. Any more? I think I got them all now. Those are all the odds. The rest are evens, which I don't really care about. Okay, now there's so many odds here. I can say, first of all, I expect there's going to be several duplications, right? You can't just make this with one duplication. You have to patch up all of these odds. So there's going to require many duplications. But since it's a path, we can leave 2 odds and then fix all the others. All right? So maybe we could decide, first of all, which odds should we leave like they are? There, of course, are many ways to do this, but actually, when I look at the graph, one of these odds kind of stands out as being a pain to fix, and that I would like to leave the way it is. Anybody agree with me? There's one odd in the picture which is a little bit troublesome to turn even. Yeah.
Would it be the bottom right of the 3 5s?
This one here?
Yeah.
That I actually wasn't thinking of that one, because I mean I could make an edge, say, right there, which makes it into a 6 and a 4. So I think that's okay.
The
So,
top 3.
yeah, the 3 on the top. What's special about that one?
There are no odds in here.
Yeah, there's no odd, which is right next to this one. All right. So if you were going to make this even, it would require 2 edges to duplicate, and that I don't like that. So because I want to duplicate as few as possible. So this odd I'm gonna leave like it is. I think the rest of them don't have that property. So I don't identify any of the other ones as being places that I like to leave like they are. All right. So the rest of them, I'm just gonna try and take them in pairs and connect them up, and hopefully I can sort of just pair them up. So maybe I'll pair up these 2. There are, of course, many ways to do this. I'll pair this 5 and a 3, this 5 and a 5, this 3 and a 3, this 3 and a 3. And then I left one other 3 all alone, which is fine. That's what we expected, right? So these became 4s here. This 5 became a 6, this became a 4, this is a 4, this is a 4, that's a 4, that's a 4, that's a 6, that's a 6. And I'm going to leave these 2 3s like they are. All right. And so, specifically, the answer to my question here, how many edge duplications are necessary? 1, 2, 3, 4, 5, right? You need to do this using 5 duplications, and it's not possible to do it in any less. So we need 5 duplications. All right. And if you actually did draw in where the parade goes, I hope you remember when you're drawing an Euler path, you have to start and end at the odds. So you would start at one of these 3s and finish at the other one. And otherwise, go across all those edges. All right? So actually, if you're the kids in the neighborhood and you're trying to predict where the parade will retrace its edges, it's actually hard to do in this graph because I paired them up in this way, but there are many other ways that you could have planned this out. So there's no guarantee that that the parade is going to go across this edge twice. In my version, my plan does have them repeating this edge, but there are other ways you could have done it, which did not repeat that edge. All right. Although you could probably predict pretty well that they were going to make this one either the starting or the ending point of the parade. If you'd like to be there at the end. The end of the parade's kind of nice because everyone just sort of stands around in the road when they're done. They don't know what to do. All right. this is all I want to say about minimum duplication circuits and minimum duplication paths. Any questions about that? Tell your family at Thanksgiving dinner you learned how to plan parades that don't repeat a bunch of roads. All right? I got some more stuff to talk about. That was not my concluding remarks. I'm just saying, you can tell your family. Although maybe since you're here, you are the ones who are not going home to your families. I don't know. That's all right. Tell your friends if you got them. I hope you got somebody. If not, you can watch this video while you're eating Thanksgiving dinner on the YouTube. Like and subscribe. We have enough time to, I want to talk just briefly about what we're going to talk about in more detail going forward. We'll just get into this. I always feel badly like on a day when people didn't show up to class. I don't know. I don't know entirely how to feel about, should I like only do half of the class and then let you go?
Yeah.
Yes.
I feel like that,
Yes.
won't you feel like, man, I shouldn't have come at all then, right?
No, it's
If
okay.
you,
We,
yeah?
It's a reward.
we learned.
It's a reward. I got the
We'll
baked
know a
goods
little
here.
bit more. Yeah, exactly.
Yeah.
I got that pumpkin bread.
Let's do another 10 minutes or so. I feel badly letting people go when they came.
Don't feel bad, man.
Yeah.
Yeah?
No, I
Don't
got
feel
some
bad.
stuff to pack in 15 minutes.
Yeah.
All right,
It's
I'm going for it. I know you don't want to. I shouldn't have said it at all because I was not prepared to
come on.
obey your wishes. What we've been talking about all along has been repeating edges in a graph, trying to avoid repeating the edges, which is what you want to do if you're the snowplow guy or something like that. It turns out a more interesting problem in the real world, there are more useful situations which involve trying to avoid repeating vertices. So this is the other big thing that we're going to talk about, and we'll just do a few minutes on this today, but this unfortunately has just like another person's name on it. This is called Hamilton circuits. And you just have to remember, Euler circuit has no edge repeats. A Hamilton circuit, this is a circuit which has no vertex repeat. So a circuit which visits every vertex, no repeated vertices. That's called a Hamilton, or sometimes Hamiltonian circuit. No repeated vertices. This is named after a Scottish, I believe, mathematician, Irish. I think Irish, Hamilton. Not the Hamilton of American history, although there is that Hamilton, the American Hamilton, came up with some things in mathematics which are named after. There's something called the Hamilton apportionment strategy, which I don't know much about. But anyway, this is not that Hamilton. This is a different Hamilton. A circuit which visits every vertex and doesn't repeat any vertices. This is called a Hamilton circuit. For example, I'll just draw a few simple examples, which we will elaborate on next time. This graph here, is there a Hamilton circuit? That is a circuit which visits each vertex without repeating any vertices. There's no Euler circuit in this case, but does anybody see how you could do a Hamilton circuit here? Can you visit each vertex without repeating any in a circuit? You don't have to use every edge. You just have to make it to every vertex. Yes? How would you do it?
I would skip the middle edge and I would just go around and make a square.
Yeah, how about around the outer? She said skip the middle edge, which is a good idea. All right? This is a Hamilton circuit. Ham circ. All right? You missed the edge. That's fine. The Hamilton circuit is not about the edges. It's about hitting every vertex. Okay? That's the idea. Here's just some more simple examples. How about this one here? Can we do a Hamilton circuit in there? Anybody see how you can do it? Actually, it is possible in this graph to do a Hamilton circuit. You got to hit every vertex. See how to do it?
Start at the middle one,
Okay, start in the middle one.
and then go around, and then come back up to the middle.
How do I get to the,
Well, like go down.
go down, okay, and then around.
Yeah.
I don't, if I go all the way around like this, then I will have repeated this vertex,
Oh.
which I don't want to do.
You could do it with the line in the box, right?
The diagonal.
Yeah.
Yeah, if I go out along the diagonal and then go around and then come back this way, I think that'll do it, right? This is a Hamilton circuit in that one. One thing that you'll notice is the degrees really don't matter very much at all, or they matter much less, at least, in this than the Euler circuits and such. How about this? If you had no diagonal there, just like that, without the diagonal, this one actually has no Hamilton circuit. I will just say, I mean, just because I said so, although it's hard to say why. It's not really about the degrees. This one had some odds and some evens, but for Hamilton's, that's not, it turns out not to be important. The whole theory behind Hamilton circuits is really completely different. If I take this one, which is kind of the same thing, but a little bit longer, actually this one does have Hamilton circuit. You can go like this. Come down here, up and around there. Like that, right? This one does have Hamilton circuit. So, when does a graph have a Hamilton circuit? And then how can you find it? These are the big questions which we will start talking about next week. And I think that will do us for today. Thank you for your participation. I hope you all have a good little break. And I'll see you in about a week.